So on the last video, we had just defined our equilibrium in terms of x. And what we were doing is we were about to plug into the law of mass action and substitute back in so that we can find x and then find the actual equilibrium concentrations. So this was our law of mass action from earlier in the problem. So let's go ahead. So we have 2.0 for K, that was given. And now we're going to substitute in terms of X these values. So for hydrogen, 2.0 equals X to the first times X to the first over 8 minus X, and that is 1 sig fig yaw, and that was from the beginning in the given, 8 molar, remember, so 8 molar minus X, that's to the first, and 8 minus X to the first. So that gives us 2.0 equals x squared over 8 minus x squared. So we have a perfect square here on this side. Now I'm going to continue over here with this. So I'm going to copy that down. 2.0 is equal to x over 8 minus x squared. Perfect square on this side. So if we want to, again, isolate x, we're going to have to, first of all, take the square root of both sides. So when you take the square root of 2, I get 1.4 equals, square root of this side gives you x over 8 minus x. Now, we're going to just cross multiply and distribute. So 1.4 times 8. And I'm just going to go ahead and round this, y'all, to 1 sig fig. So that's going to, actually, I'm going to leave it because this is one of those kind of weird ones. I'm going to leave it 11.3 for now. We'll come back later and deal with sig figs. Minus 1.4x equals x. Now let's collect our like terms. So we need to move our x's over together. So I need to add 1.4x to both sides. So that's going to leave on this side 11.3 equals x plus 1.4x, which is 2.4x. Divide by 2.4. And that leaves you with x equals 4.7. So now let's round it to just 1 sig fig because we would have, I didn't want to round it too much a while ago. So x is 5 molar. So x is the magnitude of the shift, which is a 5 molar shift. So now come back up here and substitute in where your x's are. 5, 5, 5, and 5. So that means the final equilibrium concentration of water is equal to 8 minus 5, which is 3 molar. Concentration of the CO at equilibrium is going to also be 8 minus 5, so 3 molar. Concentration of hydrogen, which is equal to X, is 5 molar. And the concentration of the CO2, which is also equal to X because they have the same coefficient, 5 molar. So these are the numbers that you would be searching for. All right, let's look at this next example. This will be our last example like this. Pause this video if you would, and then work it out and then check your answer. This tells us we have a 1 liter container filled with 0.5 moles of hydrogen iodide at 448 degrees Celsius. Then they go on to give you the Kc at this temperature. What are the equilibrium concentrations of each component? So again, we're going to ice our problem. You want to be careful on a problem like this, class, because what they've given you in the beginning is the moles per and the volume of the container. So sometimes the volume is not 1 liter. I'm going to go ahead and just kind of make a little calculation here. Concentration of HI is 0.50 moles per 1.0 liter. So that means we have 0.50 molar for the HI concentration. And I'm doing that because oftentimes, again, it's not in a 1 liter container. So you got to be careful if they give you the moles that you divide by the volume to get your actual concentration. So they're telling you that this container is filled with 0.5 molar of HI. Well, look where the HI is. That is the product. So in your initial row, initially, you're going to plug in 0.50 molar for the HI. They do not mention either of the reactants. So since they don't say there's any present, you have to write in 0 and 0. Now let's define our shift in terms of x. Now this equation is not balanced, so we do need to balance it. So I'm going to place a 2 here, 2, and that's a 1 and a 1. So it's a 1, 1, 2. Now, again, we don't need to calculate Q on this one because we have some holes over here. So it's going to shift this time to the reactants. So it's going to say minus from this side because it's shifting away. Okay, it shifts to where the holes are, and it's going to add to this side. And we're going to define this in terms of x. Now, since there's a coefficient 2, we say minus 2x. This will be plus 1x. This will be plus 1x. So in the end, 0 plus x is x, 0 plus x is x, and 0.5 minus 2x. So this is your equilibrium concentrations in terms of x. So we got to now figure out what x is and then plug it back in. So law of mass action. K is equal to the concentration of HI, now squared, products divided by reactants, concentration of hydrogen to the first times concentration of iodine to the first. They told us K was 50.5. Now substitute in these values here in terms of x. So for the HI, we're going to plug in 0.50 minus 2x, and that's squared over x times x. So we end up getting 50.5 equals 0.50 minus 2x squared over x squared. Now, again, we have a perfect square. So since we have a perfect square, we have to take the square root of both sides. So we're going to say second square root of 50.5, and that's going to give you 7.11 equals. Square root of this side gives you 0.50 minus 2x over x. Cross multiply. 7.11x equals 0.50 minus 2x. Now, collect your like terms. We're going to add 2x to both sides. And that's going to give me 9.11x equals 0.50. Divide by 9.11. And that's going to give you your x equals 0.0, I need 2 sig figs, so 0.055 is your x. Not a huge shift. So let's come back and substitute in terms of x. So here, this is going to be 0.055 molar. Iodine is going to be 0.055 molar. And for the hydrogen iodide is going to be 0.50 minus 2 times 0.055. So let's do that. And that's going to give us 0.39 molar. So your final concentration, hydrogen, is equal to iodine. Since these are equal, I'm going to set them equal to each other, which is 0.055 molar. And then for the hydrogen iodide at equilibrium, the concentration is 0.